Welcome back to CCCS122 Discrete Mathematics. This is Chapter 6, Counting. So this is the second half of the chapter, and we'll look at permutations and combinations today. So a permutation of a set of objects is an arrangement of those objects. An ordered arrangement of R elements of a set is called an R permutation. So an R permutation is basically one way to arrange R different elements. For example, let's assume we have a set S, this one consisting of 3 elements, 1, 2, and 3. Then 3, 1, 2 is a permutation, an arrangement of the elements of the set S. The arrangement 3, 2 is a 2 permutation of S. It consists of 2 elements from the set, specifically the element 3 followed by the element 2. So the order in which these elements of the set are placed matters. So, for example, 2, 3 is also 2 permutation of set S, but it's a different permutation. So the order in which these elements are placed matters. So right away, what is the number of R permutations that you can make from elements of a set with n distinct elements? Distinct elements is important to note over here. Distinct means there are no repeat elements, as is the case in a set. You cannot have 2 instances of the same element in a set. So if we have n distinct elements, how many permutations consisting of a subset of R of those elements can we make? We denote that by this function PNR, or there's this alternative notation that you'll also see, NPR. And we can calculate PNR with the product rule, which we just saw earlier. So PNR is n times n minus 1 times n minus 2 times n minus 3 times n minus R plus 1. And we'll get into the logic of this, of why this formula is what it is, and we'll see another form of it. So the reasoning is quite simple. The first element that you pick can be one of n available elements. The second element that you pick will be one of the remaining n minus 1 elements. The third element that you pick is one of the remaining n minus 2 elements, and so on. The rth element, is one of n minus r plus 1 elements. So, and then you apply the product rule, of course, and you can multiply all of these terms. And so specifically, if you have n equal to 8 elements available, and you want to know what are the how many 3 permutations are there? So we want to find P8, 3. We can find that by simply multiplying 8 by 7 by 6. 3 elements. Multiply those together, you get 336. Or another way to think about that is you think about it, the start of this sequence over here kind of looks like like a factorial function, but not quite. Doesn't go all the way down to 1. So another way to write this is basically 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 5 times 4 times 3 times 2 times 1. And obviously you can see right away that all of these terms cancel out with all of these terms. And what you're left with is this understanding, this formula that we have from our understanding of applying the product rule. But the reason we wrote it this way is that because generally the formula for permutation is expressed using factorials like this. So PNR or NPR is n factorial divided by n minus r factorial. Now, how many different sets of 3 people can we pick from a group of 6? And question is permutation the right way to answer this question? And let's see. So there are 6 choices for the first person, 5 for the second one, 4 for the third one. So that would mean 6 times 5 times 4, 120 ways. Is this correct? And this is, of course, not correct. Why? Because what I'm trying to do here is I'm trying to select a team. And in this team, it does not matter which person gets picked first, which one gets picked second. So the order of selected elements is immaterial over here. And for that reason, this answer is not correct. For that reason, using permutation is the wrong choice. Need something different for this. That something different is combination. So, let's say you pick, out of a set, you pick a person C, a person A, and a person E for a team. Now, whether you call that team CAE, or whether you say this is a team consisting of E, C, and A, makes no difference. It's the same group of people. This is one of those situations where order of selection does not matter. And that's why permutation is the wrong mathematical tool to use here. So in a permutation, these 2 cases would be counted separately. So how can we compute how many different subsets of people can be picked? That is, we want to disregard the order of picking. An R combination of elements of a set is an unordered selection. An R combination of elements of a set is an unordered selection of R elements. So an R combination is simply a subset of the set with R elements. For example, consider the set S containing 4 elements, the numbers 1, 2, 3, and 4. Then this set 1, 3, 4, and notice I'm using set notation over here. I'm using these curly brackets, denoting this is a set. And as you recall, in a set, the order in which you place elements does not matter. So then 1, 3, 4 is a 3 combination from S. It's a subset of S consisting of 3 elements. The number of R combinations of a set with n distinct elements is denoted by CNR, kind of like PNR for permutation. Or we have this alternative notation for this as well, NCR. So let's look at this problem a little more manually. So let's say we have, we want to find C42, the number of combinations of two combinations that can be picked from a set of size 4. The answer to that is 6. And for example, I can just enumerate, I can simply list all the possible 2 combinations for this particular set, and that would be all of these: 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. So, what we are still missing is some kind of closed form expression, some kind of formula for combinations. So how can we calculate CNR? Consider that we can obtain the R permutations of a set in this way. So first we form all the R combinations of the set. So there are CNR, there are CNR such R combinations. Then we generate all possible orderings within each of these R combinations. And there are PRR such orderings in each case. So it gives us PNR equal to CNR times PRR. So first term is number of ways to select subsets, and then we multiply that by number of ways to order elements of chosen subset. And that is basically what will make PNR. Now we have an expression for PNR. We can use that to also find an expression for PRR. So if I rearrange these 3 terms and substitute the terms for PRR and PNR, I can find myself an expression for CNR. Let's see how that works. So CNR on one side, PNR divided by PRR on the other side. And so I just substitute those expressions, and I get n factorial over n minus r factorial in the numerator, and I get r factorial over r minus r factorial in the denominator. R minus r factorial, r minus r is 0, 0 factorial is 1, so this basically just goes away. And what I'm left with can be simplified quite nicely into this. As you can see, it's basically the permutation formula that we had over here with an r factorial, an additional r factorial term in the denominator. And that's the formula for combination. Now we can answer the initial question. How many ways are there to pick 3 people from a group of 6, disregarding the order of picking? And I just apply this newly discovered formula for combination, makes it 6 factorial over 3 factorial, that's r, multiplied by 6 minus 3 and minus r factorial. 6 minus 3 is 3 factorial again. And I end up with 720 in the numerator, 6 times 6, 36 in the denominator. Do the division, and the answer is 20. There are 20 different ways, 20 different groups that can be picked. And there is a corollary to this. So let n and r be non-negative integers, which of course they have to be. Then c and r is equal to c of n and n minus r. And why is that? So if you want to pick a group of r people from a group of n people, that is the same as splitting a group of n people into a group of r people and another group of n minus r people. So there are just as many ways to select r people as there are to not select n minus r people. So when you're making your selection for the group, you're automatically selecting people who will not be in the group. And the number of ways to do that is equal, of course. And that's what this corollary states. So there's a simple proof for that. You can, of course, simply start with what we have on the right-hand side, C combination C of n and n minus r. Substitute that into the formula we have, n factorial in the numerator, n minus r factorial times n minus r factorial. These two conveniently cancel out. These two negative signs make this a positive, and what you end up is this, which is exactly the formula for combination for C and R. And like I said, if you want to see that through an example, let us consider again the same set of 6 elements, n equal to 6. You want to pick 2 elements, and that will leave 4. That is essentially the same as picking 4 and leaving 2. In either case, the number of choices is the number of possibilities to divide the set into one set containing 2 elements and another set containing 4 elements. And that's why these two are equal. Here's an example. A school's spelling bee club has 8 female and 7 male members. For an upcoming competition, the coach wants to have 6 female and 5 male members on the team. How many possible configurations are there? So we have to pick basically 6 out of 8 female team members, and we have to pick 5 out of an available 7 members for the team. Both choices can be combined. So you can think of the selection of female team members as task 1, and the selection of male members of the team as task 2. Both tasks can be performed independently, which means the total number of possible configurations will be the product of C86, number of ways I can pick 6 female members from 8 available, and picking 5 male members from a group of 7. Apply the combination formula here. So 8 factorial over 6 factorial times 2 factorial, and 7 factorial over 5 factorial times 2 factorial. Do the math, simplifying, you end up with 588 possible team configurations. Another example. How many ways are there to choose a committee of size 5 consisting of 3 women and 2 men from a group of 10 women and 7 men? It's basically the same problem that we just saw. Now for a committee. Number of ways to choose 3 women out of 10 is C10-3. The number of ways to choose 2 men out of 7 is C7-2. And the number of ways the committee can be made is then just the product of these 2 numbers, which in this example comes out to 2,520. A class has 20 women and 16 men. In how many ways can you put all the students in a row? So, in how many ways? It means that we're talking about order. Okay, so keep that in mind. Sequence, order will matter here. Put 7 of the students in a row. Put all the students in a row if all the women are on the left and all the men are on the right. So, first one is easy. There are 36 students. You want to put all of them in a row. We don't care. We don't care about genders. So, 36 students, 36 factorial ways. 36 students for the first position, 35 for the second position, 34 for the third position, 33 for the fourth position, and so on. So 36 factorial is the answer to the first question. For the second question, putting 7 of the students in a row. Now we're selecting a subset, and order is mattering. 7 out of 36, because again, we don't care about gender over here, so we're treating the whole group as a group, 36 students. So the answer is P36, 7. Apply the formula, figure out what the number is. Finally, how can we put all the students in a row? But here now we care about gender, so all the women on the left are basically in one group, and all the men on the right are in another group. So, in how many ways can we order all the women among themselves, and in how many ways can we order all the men among themselves? And once we have those numbers, it'll be the women on one side times the number of ways we can arrange the men on the other side. And so the answer to that is 20 factorial ways to order all 20 students, women students, and 16 factorial ways to arrange all the men students. Okay. That gets us close to the end of this chapter. So there's related to combinations is Pascal's identity. Let n and k be positive integers, which, when we're dealing with selecting items from a set, which we always are, there can never be a negative number of elements of a set, right? You cannot select the negative number of elements from as a subset. So n and k, yes, are both positive integers. N has to be larger or perhaps equal to k. So then C of n plus 1 k is equal to C of n k minus 1 plus C of nk. Okay, it looks pretty abstract. Let's see if we can explain this a little. So, or prove it perhaps. So, say we have 8C2, choosing 2 from 8. That is 8 factorial, 8 minus 2. Oh yeah, 8 minus 2 factorial. 2 factorial, do the math, you end up with 28. 10C3. 10 factorial over 10 minus 3 factorial, 3 factorial. You can simplify that into, evaluate that to 120. 7C3. 7 factorial over 7 minus 3 factorial and 3 factorial. These terms, some of them will cancel out and evaluate to 35. 7C4. Terms cancel out and this evaluates to 35. Now, a set S that contains n elements, so set S over here is this inner set, okay. Set S contains n elements already, and we define another set T containing all the elements of S plus one additional element. So set T, if set N contains n elements, set T contains n plus 1 elements. All the elements of S plus a new element that we're even naming small a. So you can calculate C of n plus 1, okay, basically selecting k elements out of this larger set T. And you can think of that as equivalent to answering the question, how many subsets of T containing k items are there? And there are two ways to select a subset of T. One, basically choosing a subset of k minus 1 elements from S and then adding to it this new blue element A. And the answer to that is, of course, C n k minus 1. So that's C. So basically choosing k minus 1 elements out of n and then having no choice but adding A to that. So this is how many choices we have to do that. The other case is we select a subset in which all k elements, in which this element A over here is not chosen, which means all k elements are picked from inside of set S. So this chosen subset does not contain A. And there are C and K ways of doing that, selecting all k elements from within the n elements of S. Those are the two options. It can happen one way or the other way. There's no overlap. There's no way to both select A and not select A. And that's basically where we can apply the sum rule. Case 1 and case 2, and just adding up the different ways of doing that. And that gives us the number of ways you can select k elements from n plus 1. In Pascal's triangle, each number is the sum of the numbers to its
upper left and upper right. And you can see Pascal's triangle, we can see Pascal's triangle to the right. We begin with these numbers at the top. We always have ones going down on the sides. So you can see over here that this 2, for example, is the sum of 1 and 1. This element 3 is the sum of 2 and 1. This element 6 over here is the sum of 3 and 3. 3 over here is the sum of 1 and 2. The 4 over here is the sum of 1 and 3, and so on. And this goes down all the way to infinity. Now there's an interesting relationship between Pascal's triangle and the coefficients, the binomial coefficients, and I'll show you that now. So C00 is 1, fine. C10 is 1, C11 is 1. So we have n along the vertical axis, and we have k changing along the horizontal axis. So 0, 1, 2, that's k changing, and 0, 1, 2, 3, 4, n changing along the vertical axis. Now, if you look at the values of these combinations in blue, check the pattern. We have 1, 1, 1, 1, 1 over here, 1, 1, 1 here on the sides, and right in the center, in the third line, we have 2. In the next row, we have 3, 3. On the fourth row, we have 4, 6, 4, which is exactly what we saw over here in the Pascal triangle. So the coefficients of combinations, when arranged in this way along this n and k axis, basically form a Pascal's triangle. These expressions each are also called binomial coefficients. And why is that? Well, if you take a plus b to the power 1, a plus b to the power 1, you just get a plus b. If you take a plus b squared, if you open that up, expand it, you get a squared plus 2ab plus b squared. Now pay attention to the coefficients in front of these terms over here. We have 1 as the coefficients over here. For the square expansion, we have coefficients 1, 2, 1. And look where we saw that before. 1, 1, 1, 2, 1. And guess what? What comes next? 1, 3, 3, 1. And when you expand the cube, you get coefficients of these terms 1, 3, 3, 1. And when you expand the fourth power, the coefficients are 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. So you can see that these coefficients over here that you get from the expansion of different powers of a plus b, again, the different rows correspond to the different rows of the Pascal's triangle. So a plus b, expand it, simplify it, get this thing over here. A plus b cube is the expansion done step by step, gets you 1, 3, 3, 1 over here. Of course, you have to arrange these terms in the right order. So here we're doing it in decreasing order of powers of a, okay? Or you can do it in powers of b, doesn't matter. So there's only one term a cube because there's only one possibility to form it, right? Where a gets multiplied with this a gets multiplied with that a. And so on. So there's only one way to do that. There are 3 ways you can select a. You can select 2 a's. and only one B, and so on. You get the idea. And this gets us to the generalized formula for the binomial theorem. So you can basically write the formula for the nth power of a plus b like this using combination coefficients. And that is the end of chapter 6. And I'll see you again in the next chapter, chapter 7.